All right, now we come to an important discussion for which we have been working towards, which is what can we get from a moment curvature curve? What is the value of this? How can we use it? Okay, now that we understood how it is generated and how it is based on various parameters and all of that stuff, how can we use it? What can it give us? And actually, last time in my graduate class, I gave this challenge to my students that find as many points as you can from the moment curvature curve. And it was surprising that very few could be identified. But we will see here today that there is a lot that we can get from the moment curvature curve. And most of them are hidden in plain sight, as they say. So for this one, I'm going to use the CSI call program for this demonstration. As you know, CSI call is developed by CSI. I have worked on this program for many years as one of the developers, and it's also based on my book on cross-section, behavior of cross-section. So it's a combination of my class notes plus the CSI call and plus the book that me and Dr. Fawad have written together. So let's talk about this one. So we're going to look at 4 categories of things that we can get from moment curvature curve. Things that are right on the curve immediately. Things that can be derived from the curve from additional computations. And then what is under the curve? And then finally, what can be retained in the computing process during generation, which we can then output as additional information. So these 4 things, because CSI call was developed by us, by our team, then we could actually output a lot more information from that program. And also you can see the same thing in SAP and ETAP section designer as well. So items on the curve. Let's see. This is the typical moment curvature curve. And you can see here there is a yield point kind of, and so we can see here, first of all, the first cracking moment can be determined where the slope will change suddenly. Second one is the yield moment that can be determined, and then an idealized curve can be made from there. And then we can determine the ultimate moment, mu, and then you can get the ultimate curvature, which is the residual moment, which we can define at a certain level, 80%, 75%, whatever level of the maximum. And then we can get from using this, you can get the residual strength ratio from that. So we already got, as you can see, from 1, 2, 3, 4, and 5 items from the curve straight away without doing anything, just by looking at the curve. So that's the first one. Then let's go forward. Then we get the curvature. That was moment curvature. You get the yield curvature, you get the maximum curvature, you get the ultimate curvature, which is some fraction of the maximum curvature, and then you get a ductility ratio, which is the ultimate curvature divided by the yield curvature. And this ratio is so important to design members because we are trying to target a ductility ratio of, let's say, 8, or 10 or 5 in a good way. So you can see how much did we get. So this is very good, very, very, very important information that we can get from the moment curvature curve, again from the curve directly just by looking at the graphics or the values. So because we got the ductility from the moment curvature curve, we can now complete the cycle of the ductility levels. We can get material ductility we got from the stress strain curve, which we were able to change by confinement, moment curvature ductility, rotation ductility, and deformation ductility. All ductilities can now be computed because we have linked the material ductility to the next levels. And then from there, it will be, we can discuss that in another talk. So that is the benefit of the ductility that we just found from that curve. Now, let's come back. Performance level. In the performance-based design, which we have talked about a lot in other talks, the important things are these values on deformation. So we can draw a line and say, okay, this is immediate occupancy level curvature or deformation. This is the life safety level. That is the collapse prevention level. So you can see here, you can get 4 more items, or we can define 4 more items on that curve, and we can corresponding moment, corresponding strain, everything can be determined from there. So the performance-based, this is the foundation of performance-based design that we are setting up here, and that can start from the moment curvature, or curvature curve, or rotation curve, or the displacement curves, and so on. But curvature obviously is the starting point. Normally we put it on rotation, which is a derivative of curvature. Now let's look at the items which are derived from the curve with some computations. So the first one is stiffness, because as I mentioned to you, from the curve we can determine the slope of the curve, and that slope is the stiffness. And it's so important because this stiffness is real. It is not gross, it's not cracked, it is not equivalent, it's not something. It's the actual stiffness that we were able to determine through nonlinear behavior of cross-section as well as materials. So this stiffness can be determined at any point along the curve for any value of moment or any value of curvature. That's the important thing. And stiffness now is very important. And as I mentioned, we can get this curve and then we can determine the stiffness from there. And the stiffness can now include all these effects, which are not possible. The traditional E or traditional I or traditional EI cannot include all these effects that we can include now in the moment curvature curve. So all the effects that we include in moment curvature curve automatically give us the ability to include in the stiffness determination. So our stiffness can now be pretty accurate depending on all of these factors. Let's now look at a simple numerical example. Let's say this is a cross section 1 meter by 1000 by 600 millimeter with reinforcement, and the E, traditional E, is that much, and the traditional I we can calculate from BD cubed by 12 is that number. This is the gross stiffness based on the traditional computations. How does it compare with the stiffness that we are talking about? So that EI will be that value, and now that is EC for concrete, that is ES for steel, that is not single value, cannot be used. So then this computation already is wrong because it's using concrete, whereas this is a reinforced concrete section with two materials. So how did we incorporate ES into this computation? We didn't. We just ignored it. We assumed this as to be a gross section only of concrete. So that's already kind of a big miss that we did in this computation. And secondly, that section could be cracked. So that I has no meaning when the section is cracked. That is only based on completely uncracked section. But in deformation, immediately when you apply moment, cracking will happen. And so that means that stiffness that the I that we determine also has no meaning. So this whole stiffness actually has no reliable use except for a starting number, unless it is modified by stiffness modifiers and so on, which is completely another subject for another time. So because of that curvature, this will be modified. So that means this stiffness computation is not very useful for the purpose of the work that we are doing. But we can determine this from the curve more reliably. And not only one, we can determine many types of stiffnesses. First of all, we can get the initial stiffness, which is the initial slope, which will be similar to the gross stiffness, roughly, except that we have steel included in this one. And then we will have the secant stiffness of any point with respect to the origin, and the tangent stiffness, the slope of the curve at any given point on the curve. So three stiffnesses straight away can be determined from this curve, each one vastly different and with vastly different application. So most often secant stiffness gives, many people feel that secant stiffness is more reliable number to work with in nonlinear analysis and convergence, because tangent stiffness can become negative or become zero, which is a computational difficulty in some models. So if you compare the stiffness change with curvature, because it changes with curvature, let's compare it. This is the plot that you might get. Of course, it will depend on many things, but roughly you might get this one. The green line over there is the initial stiffness. And then we have the tangent stiffness. Of course, initial stiffness is kind of constant. And then the secant and the tangent stiffness will vary with curvature like that. So immediately, as soon as we have an even small curvature and concrete cracks, then we lose this majority of the stiffness. Of course, reinforcement will come into play, but we can see that the majority of stiffness is lost, and then the tangent stiffness becomes negative at some point, whereas the secant stiffness remains positive but becomes very small. So for a large curvature, when only the neutral axis depth is, for a beam especially, it will be very small. The stiffness is a fraction of the initial stiffness, real a fraction, you can see, and it drops rapidly. But this plot can indicate that the stiffness determination especially for beams without much axial load will be like this, and without much reinforcement. And this can be affected by many things, as we have discussed earlier. But this gives you an idea that the initial stiffness that we calculated, or the gross stiffness that we calculated, has no real relationship or real sort of insight into the actual stiffness after deformation. So you can plot them, stiffness, reduction, and cracking factors based on this one, because you can calculate it. So you can see from here a cracking factor of about 0.5 exists at this yield point roughly, and at that point 0.35 when you have the cross section like that for a beam, and for a column roughly 0.4. They are quite similar to the cracking factors used by some of the codes. So the codes cracking factors, the initial cracking factors, are not so off in these computations, especially at the onset of the yield. Of course, after that, they do not have much meaning, but at least they try to capture this important reduction in stiffness, and these factors appear to be, from this example at least, to be similar to what the codes use for initial cracking factor on the gross stiffness. The thing which is a bit funny to me, and I have discussed this often, the variation of these cracking factors across codes. You can see here the factors are so much different, 0.35 to 0.7 to point, and there's a huge variation of these. So the codes do not agree on what is the level of cracking, or what is the level of stiffness reduction we should use in our analysis purposes. And the only way, of course, is to do the real moment curvature determination and use that value. But as you can see here, there's a huge variation in the code-specified stiffness factors across these 10, 15 codes that are compared here. So stiffness types, beyond that, we can have gross stiffness, initial stiffness, crack section stiffness, secant stiffness, yield stiffness, post-yield stiffness, tangent stiffness, plastic stiffness, residual stiffness, and so on. So just stiffness has like 7, 8 further variations. So if you add this 7, 8 stiffness variations with 7 to 8, 10 items that we found earlier, we are approaching 20 items already from the moment curvature curve that we can get more reliably than the traditional methods. So coming back to this one, so you can, from that one, you can also get the crack spacing because it's related to strain. So strain can be multiplied by a distance, and we can get crack width. So with the crack spacing, we can get the, if we specify the crack width, we can get crack width, or we can specify this crack spacing, we can get the crack width, and the other way around. Width versus spacing and spacing versus width, because the strain is available at every curvature level. So that's another way to sort of estimate. This will not be very accurate. It's just roughly an idea that what is the approximate relationship between crack width and spacing for a particular curvature. This is, cracking is a very complex phenomena, so it cannot model accurately, but we can just get some rough idea from there. So we can see here, going back from this one, we can complete the cycle now, moment, rotation, and displacement using the actual stiffness, not the assumed gross stiffness, but the actual stiffness can be used to now compute the results that we saw in our beam that was loaded in the lab. And so we can calculate from the moment curvature curve like stiffness, deflection, slope, strain, and all. The important thing is deflection, because the most important variable in the deflection computation is EI, which is grossly incorrect if we use gross. So if we use the reliable stiffness from the moment curvature curve at every moment value, especially if the moment is large, and it's already beyond in some portions beyond the yielding, it's varying, we can use this to compute after the cracking especially, then we can use this to compute the deflection much more reliably than any other approximation. So rotation, which is an integral of the curvature, we get that. And from there, deflection, which is an integral of the rotation, we get that. So by integrating the curvature, we get rotation. Integrating the rotation, we get displacement, and we can determine deformation. Of course, for a structure, we can run more full finite element formulation, which I will mention towards the end of the talk. So the procedure to measure deflection using moment curvature curve or compute deflection using moment curvature curve is use the cross section and axial load, generate moment curvature curve, plot the moment and axial load diagram, read the curvature along various locations, and so on. So axial load diagram or moment curvature diagram, and then we can read that and calculate the m over ei, and then integrate out over the length, because moment will be varying, curvature will be varying, so the stiffness will be varying. Not single value can be used. Normally, in the traditional deflection calculation, we assume the same value of stiffness through the entire length, which is not the case in real deformation. So cracking point, yield point, failure point, ductility, slope, stiffness, all of that, deflection, strain, and crack width, I just summarized quickly. 9 items here, plus a number of items that we got earlier can be determined. Now, let's look at what can be done while the curve is being generated by computing additional information, which may not be obvious or which may not be easy to determine from the curve when it is available. But while we are doing the computations, we can save some data and we can output that data, and that could give us further insight into the cross-section. So the first thing is that we can note every point during the generation and say, okay, what is the state of the cross-section, strength, stress, strain at each point? So we can know what is happening to the section while it is deforming. So we can say concrete cracks, we have the state preserved at that point. So we have the stress strain curve and the neutral axis depth or the crack location. First bar yields, we know where it does because we are monitoring each point. So we can find this point, the first bar started to yield at the bottom. Concrete crushes, outside the cover is crushed. Here, as you can see in this figure, the core is still intact. So we can determine that from that because we save all these points and this information. Stress strain in every material is saved at each point. You can go back and read those numbers to further understand what's happening. And then the residual strength is reached, everything is almost gone, so we reach the final value. So we can see that we can get these properties, and as I mentioned, we got this from CSI call. You can also look at every point along the curve, you can plot the concrete strain variation in 3D and also in 2D. Like for example, from here, if you go like that, you can just vary this one at any given point, and you should be able to plot the variation of the concrete strain at any curvature. So that's a very nice way to look at the numbers and also to look at the plot, and you can look at the bar stress. You can also look at the various other items you can see. So we can move over the curve and we can see the bar stress is varying as we hover over the moment curvature curve. So that's another interesting thing that we could get because we save this information while generating it. So we can also get the concrete stress in 2D more clearly. So as you go up, you can see where it cracked and which portion is how stress, what is the value of the stress at each location. And then this is an unconfined concrete. So we can see the plot until it fails. You can see the top, the concrete failed, then the middle portion failed, and everything is gone. So we can see exactly how concrete started to fail. It started to compress or crash at the top. And then finally, the whole cross-section in compression is gone after yielding of steel. And then same thing for the confined concrete. And then we can see the concrete stress in this one here. And same thing we can see even as a plot of the stress over the cross-section. And you can see that this approaches the stress strain curve as it reaches the value close to the value, and now the whole stress is gone. Everything, all the stress is reached, and then there's no more stress block left, and the cross-section is gone. So you can see it in 2D, you can see it in 3D, you can visualize how the stress strain curve actually traversed on the cross-section until it was no more. Steel stress, same way, we can see that variation along this one in 3D. You can plot that, and you can see how it is varying, as I mentioned earlier also. So there's a lot of information that we can get by simply moving the cursor on the curve and noting down what's happening to the cross section. So let's look at the confined one. This will be more interesting because now the concrete has two parts. the red part, or the, which is the confined part, and the blue part, which is the unconfined part. And if we look at the plot of the stress strain confined, then we can see from here that now we should see a different behavior between the two models. The stress is different for the same strain because the stress strain model is different. So you can see here already we can see the difference between them. And when it cracks, over there, and then after that, when we go up, the cover is gone, the core is still intact, and we can see from here that, okay, now the core is the one carrying the compression. Cover is already gone completely, and finally the core is also gone as it reaches its compression capacity. So this is a very good way to simulate and understand the cross-section as it deforms and undergoes large deformations and large curvatures. And we can do this in 3D also, just to get a better idea. Same thing, in 3D, the two curves are separated because there are different models, and we can see here the outside is confined in the beginning. They have the same strain. Now you can see here that the outer cover is gone, and the inner core is still, because it has a high capacity, is still intact, and then finally it also reaches its capacity and is broken. So we can now see very clearly how the cover will break down first, and the outside, as you can see from here, the cover is gone first, the outside, and these are just plots of the stress strain curve, because we can basically replicate that, but now this is used in the computations to do the curvature. So everything is kind of connected. We can also see it from and this is an interesting plot, because when you bend the cross section on an angle, not on one of the primary axes, the capacity will reduce a lot, because concrete will crush very quickly in this case. And in this one, as you can see from here, that when you see that, as it go up, the portion of concrete in compression reduces significantly, so the capacity will be much less, moment capacity, and also the curvature capacity, as it drops from here, that portion in cover is gone, more cover is gone, and then only small portion is left in the middle to carry, and finally that will also be gone. So that's the plot. This is the information that you can get on top of that. So you can get concrete force, steel force, strain, nuclear axis depth, all along the variation of the strain. This is a lot of information, as you can see here. Probably you won't need that in a traditional design, but for evaluation, all of this information can be useful. And for seismic evaluation, you can now know the stress in each bar. You can know, the steel force in each bar, concrete force, nuclear axis depth, everything on every curvature point and corresponding moment. So this is, I think, is a tremendous amount of information which could not be possible by traditional capacity-based design only. This is for another section, just a beam. This is for a column. This is for a beam, so we can get these variations. And you have many interesting observations here. Here, concrete, you can say force, steel and concrete force are equal. In the previous one, you have the concrete force, and there, because we have two models, so it's not directly equal. And here is only one model. So now let's come to the kind of last part of the discussion on what we can get from the moment curvature curve. What is under the curve? We have seen what is directly on the curve, what can be computed from the curve, and what can be computed while the curve is being generated. Last part of the discussion on this one is what is under the curve, which is quite interesting, and I think is not discussed enough. So what's under the curves? The stress strain curve for material, the moment curvature curve for the cross section, and load differential inversion curve for the structure. What is under that? Obviously, energy, because the area under the curve represents energy. And this is represented energy per unit volume for stress strain curve. Strain energy units is strangely, the same as the moment, but that is coming from the energy equation. So you get the area under the curve will give you, this is the elastic strain, you can say, and that is the elastic strain. If we went forward and there was no yielding or there was no ductility, that would be the strain that would be stored, and that would be a very large strain, so it would break suddenly, but that is the area under the curve, which is the actual strain energy under the material stress strain curve. So this is what we have over there. Energy area under the moment curvature curve is the energy per unit length, flexural energy, because that's the strain. This is related to flexure. So we have flexural energy, and then same thing. It's the portion under the curve, that point we can determine, and that is the elastic if it goes straight, and that is the ductility. So energy reduces. Because energy reduces, that means the failure will not be sudden, and the release of energy will be less. It will be less catastrophic. So that's the elastic strain energy, which is before the yielding. That's the equivalent energy if it was elastic all the way, and that's the total actual strain energy under the curve with the ductile behavior. So that's what we are trying to. Now we can get this information also from the stress strain curve, also in the moment curvature curve, and then we can go all the way to total energy and energy per given length, energy per length, and energy per volume, and so on. So you get all these energies, which is a very good measure of structural response. In fact, when we do performance-based analysis, one of the output that we are looking for is the energy dissipation or energy coming from various parts. So this is what we get under the curve. Let me discuss another aspect of moment curvature curve, which is often, once again, not presented in various discussions, and that is the axial load moment curvature interaction. We know of the axial load and moment interaction through the interaction surface and the PM diagrams, but we don't really look at the axial load versus curvature, moment curvature relationship diagram. So I want to look at that with you. And so basically it looks like that. It's a funny diagram, kind of, but it's an interesting one because it shows a lot of information. First of all, so in this one, the vertical axis is the axial load, and the horizontal axis is the curvature, moment curvature. And then you go here, and then you can see from here. So it resembles the axial load and two moment diagram, and you can see. So you can see the curvature variation along the cross section in the plan, and also along its variation of the axial load. As you can see, as the axial load becomes higher, then it becomes more uniform. And the reason is that in the beginning, when the cross section has no axial load, the corners, this is for a rectangle section, corners will break first quickly. So as soon as you tilt the bending moment a little bit, the corners, the curvature capacity reduces. But as you come up, and the whole core is compressed, so the effect is much less. So from this one, we can also get the curvature capacity. So we plot this one. This is a curvature capacity at any given point, and this one you can see the axial load. They are very similar in terms of how so that's you can get the moment load interaction curve, and you can also get from here you can get the curvature axial load plot in a similar manner if you cut the curve, the plot vertical slice. And if you cut the plot horizontally, you get that curve, the interaction between two moments. And similarly, if you cut the plot horizontally, you get the curvature plot on the various axes along the cross section. Now, let me come to conclude this discussion and see how all of this information can be useful in real analysis. And that is something that we have discussed earlier, but I want to make the final connection between whatever we discussed and what is the final application of this one, and especially in seismic analysis or seismic evaluation. So this diagram is actually representing this whole picture, I would say, concisely. So let me start on the left-hand side. Left-hand side is steel and concrete stress-strain materials that we have seen earlier. It goes to the cross-section. We generate the moment curvature curve that we have shown earlier. From the moment curvature curve, we get the moment rotation curve. Those moment rotation curves are assigned here in the structure to the hinges, or the portion with it that we say plastic hinge that we allow to yield. So we assign that this one here. We can also assign the whole fiber hinge to this one with the corresponding material. But let's say we are using the moment curvature for now, so we bring that here. So the structure is on the beam. We assign those hinges, each determined from the material and cross section at that location, and then we have this data. On the other side, from the earthquake side, we have the response spectrum. We can convert that into ADR response spectrum. And then from this point, we create a pushover by pushing the structure through loads and doing the nonlinear analysis of those locations, calculating the stiffness from the moment curvature, moment rotation curve, and not from the fixed formula. When we get that pushover curve, we bring and match them together, and we get the performance point. So this is the kind of a traditional method of doing performance-based evaluation. Of course, now most of the time we use full nonlinear time history analysis, and we use more advanced, but this is still very useful to do a push over analysis to understand the nonlinear behavior and how it will interact with the demand or how it affects the demand. So this is the kind of a one summary of where the moment curvature fits into the overall evaluation of structure, or the evaluation of the seismic response, or any load which goes beyond the traditional load. And we can use now the same thing to go back to our beam and can compute all the quantities that we wanted to compute. So let me just show that slide again. So finally, let me go back to the slide that we started with and see how many of those information we can obtain, because we have moment curvature curve that I started with saying that we can't do with traditional strength design. So maximum capacity we can now compute, because we have the moment curvature curve. What will happen when it reaches the capacity? We have all the information about the cross section before and after. I've shown that through that. And where it will crack, we have already, if we model it at various location moment curvature curve, we can then determine where the cracking will occur, because we have modeled the cracking in the moment curvature curve. How much it will reflect, we can calculate the deflection using moment curvature curve, as I showed you earlier. And then will it fail in shear bending? Let's say we fix that it will not fail in shear. Can I control it, how it fails? Yes. If it's an indeterminate structure, we can determine where we want the moment capacity to not yield, or where it will yield first, because now we have a way to determine that through the pushover analysis that I showed you earlier. And then we can also use that to efficiently size the cross section and the reinforcement, because we know where the critical points are and how the capacity will work. So that kind of concludes the discussion on moment curvature curve for now. And I do hope that this information will be helpful in moving forward to create more comprehensive analysis methodologies, as well as to evaluate the structures in more realistic manner. Thank you.